SCRs, or silicone-controlled rectifiers. In this presentation, we're going to be looking at what's inside an SCR, how it functions, and a few introductory calculations into phase angle gate triggering. Well, let's get going. Now, like most electronic components, SCRs are manufactured from silicon carbide. The layering and use of P and N-type silicon is similar to that of a bipolar junction transistor, or BJT. Here's a comparison between a BJT and an SCR. You can see that they each have a third terminal. On a BJT, it's called a base, and on a SCR, it's called a gate. On a BJT, we refer to the two input and the output as the input's the collector, the output's the emitter, and then on the SCR, we have an anode and a cathode. There is also more junctions than on a standard BJT. We have 1, 2 PN junctions. Here we have 1, 2, 3. And due to that, it makes for a much different operational component. An SCR shares many of the same characteristics of a BJT. It has PN junctions and is polarity sensitive. An SCR is similar to a diode as well, in that it conducts current in one direction only. It only conducts when a momentary pulse of current is applied to the gate, and it continues to conduct after the pulse until the current A to C drops below the holding value. An SCR can be thought of as a latching relay. Power applied for a moment to the gate terminal will engage the latch, holding the power contacts closed, which are representing of A to C. An SCR has two distinct circuits, a gate circuit and a power circuit. The two circuits share a single path on the cathode end of the component. A momentary pulse of current applied to the gate terminal controls when current flows from the anode to the cathode terminal in the power circuit. The value of current required to flow into the gate terminal is provided in the component's datasheet. And since the gate current is pulsed, there is little significance in determining the total current present in C, or the cathode, which would simply be the anode plus the gate. Now, once an SCR has been gate pulsed on, load current will flow A to C. This current will continue to flow until the value of it drops below the holding value. Well, let's gate pulse this SCR. So I'm going to just go here and there we go. Look at that. We got some gate current flowing for a moment. And what that allows for is current to flow A to C. I can remove the gate current here, and it continues to flow A to C. So this is a very efficient type of control device when compared to a BJT that continually needs current fed into the base terminal. This simply needs a momentary pulse of current into the gate. Now, holding current is the rating on the component's datasheet. If the current is above this value, it will continue to conduct. So that means the red arrows, they need to be at least equivalent to the holding current rating of this SCR. If the current drops below this value, the SCR will act as a switch and stop conducting A to C. The act of stopping conduction of load current is referred to as commutating in an SCR. Now, there are two different types of commutating: natural commutation and forced commutation. Natural commutation, an SCR is turned off by the dropping of load current due to a sine wave of an AC source. Forced commutation, the SCR is turned off by reversing a voltage or diverting load current using an external circuit. So why don't we take a look at forced commutation? It's going to be pretty basic here. I'm going to, there we go, break the circuit. And what I've done there, since it's an open circuit, there is zero current that flows. And I have now force commutated this DC circuit with the SCR. I can reconnect it, but the SCR remains commutated until the next gate pulse is applied. Now, like a diode, an SCR is only capable or able to conduct when positioned so the cathode terminal is negative. When the cathode is positive, the SCR will block regardless of the gate terminal being pulsed. Like a diode also, an SCR has a peak inverse voltage that should not be exceeded. If it is, current will flow in the reverse direction, causing damage to the component. SCRs can be operated in AC or DC circuits. We've kind of already seen one in a DC circuit, but let's see it again because it's so exciting. So there's the gate current for a moment, there's my load current, and I remove the gate pulse, and look, the current continues to flow in the power side and load current, and that switch, well, the light continues to stay on. Fantastic. Now the load will remain on until the load current drops below the SCR rated holding value. And so while there is applications to commutate in a DC circuit, we're not going to go into that in this presentation. As the name implies, the main use of SCRs is to provide variable or controllable rectified DC voltages. And if you remember back, a standard diode rectifier is not controllable. If it's a half wave or a full wave, you're going to get the DC voltage that it produces. You have no control over what the magnitude is. When an SCR is in an AC circuit, from anode to cathode, the gate is still triggered by a small DC voltage source. The cathode and anode are in the AC circuit, and the SCR will be forward biased for half the sine wave cycle and reverse biased for half the sine wave cycle. The gate must therefore be triggered when the SCR is in the forward biased region of that sine wave cycle. So, in this example, the gate must be triggered between 1 to 179 electrical degrees. Otherwise, it's then going to be reverse biased in the downward loop or alternation of the sine wave cycle. So although we could, try to time it so that we hit it at the right time, obviously that is not going to be the most effective, efficient, or common application in the field. Instead, we're going to use automatic gate trigger control units. These are going to be able to trigger the gate at precisely the exact moment of time necessary during the positive alternation of a sine wave cycle. Since the SCR only conducts for half the cycle, the load will then see some form of unfiltered DC voltage. So for single-phase half-wave rectifiers, it's a diode and it's uncontrolled. With a 120 volt AC system, the peak value of voltage times 0.318 would give me my average DC value, so 54 and change volts. When I have a single-phase half-wave rectifier with an SCR, it changes. And that's because now I can choose when I want to fire that SCR and conduct through the sine wave alternation. I could trigger it here, right at the beginning, in which case it would be almost identical to a standard diode. I could also trigger it here, 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 or almost at the end of the sine wave alternation. I can use a basic formula in order to calculate this, and that's handy because then it tells me that, from all the way from like 1 degree to 179, I can control the voltage, the average DC voltage from this rectifier now. It's a controllable half-wave rectifier. Now here's an example or an image that shows gate firing angle and the amount of conduction that then occurs. If I wait very late to fire and conduct the SCR, it means that only a short period of time will it conduct for. That means a fairly low voltage. If I fire the gate very early, then that means I have almost the entire alternation that is being conducting. That means the earlier an SCR is triggered, the larger the rectified average DC voltage. The SCR, remember, will naturally commutate once it reaches zero because, well, the sine wave voltage will reach zero, and that means the current that flows through the SCR, C to E, will drop to zero. So here's an example, or at least the breakdown of the equation. Emax is in reference to the maximum or peak value of voltage in the AC system, 1 plus cos of the angle. What angle are we firing at? And we divide it by 2 times pi. Make sure to put the brackets in there, and that will give you the DC average voltage generated by this controllable SCR. Remember, Emax is equal to ERMS divided by 0.707. So if we take a look at a gate trigger or phase control angle comparison on a 120 volt RMS AC system, if I fire it at 5 degrees, the peak value of voltage is 170, and I'm going to do 1 plus cos 5, and then divided by 2 pi. That gives me 54 volts DC. If instead I fire that at 45 degrees, well, then my voltage is going to go down. And the later I fire, the lower the voltage gets, until eventually, well, At 180 degrees, it's pretty much already commutated simultaneously. Now, SCRs can be used to build controllable half or full wave rectifiers, although this presentation is really only going to cover the voltage calculation for half wave systems. So here's an example of a biphase full wave SCR controlled rectifier. It's got 2 SCRs in there. And here's an example of a full wave bridge that then has a gate trigger controlled SCR in series with the DC load. Now, there are 2 methods for SCR phase control. One is referred to as resistive, the other resistive capacitive. Resistive is only capable of firing the gate between 1 to 90 degrees, whereas resistive capacitive is capable of from 1 to 179 degrees. If we take a look at the angles here on the alternation, positive alternation of our sine wave cycle, we can see 0 to 90 degrees. So it's somewhat limited, although it is a very basic arrangement or circuit. This is the gate control. It's a variable resistor with a diode connected to the gate terminal of my SCR, and they're both supplied by the AC supply. So this means it could go all the way from, almost 1 degree up to 90 degrees. That's it. On the resistive capacitive trigger, we have the capability to go from 1 to 179 degrees, and that means I have full control. It requires 2 diodes, a variable resistor, and a capacitor. You can see where the load is connected, and they're both supplied by the AC supply here. So that means I would have full control from full power down to almost 0 power. SCRs can also be used to control both the negative and the positive alternations of an AC sine wave. By placing 2 inverse parallel SCRs across the AC supply with identical controllers, I can then fire the gates at simultaneous angles for the positive alternation and the negative alternation. This type of system is used in different applications like soft starters and airfield lighting constant current regulators. This is referred to as inverse parallel SCRs. Both the positive and negative alternations are controlled at the same angle, and the frequency is unaffected. We can test SCRs with the diode function or ohmic value of a multimeter. What is imperative, though, is that you have a multimeter that has a high enough voltage of battery. If we go K to A or A to K, we should get OL, and that's because there is no conduction in an SCR unless we have gate current that is pulsed. If we place the positive to the gate and the negative to the anode, it should still say OL, and remember OL indicates infinite resistance. If we instead apply the negative to the gate and the positive to the cathode, that should give us a very low ohmic value, as well as reversing these connections. SCRs come in many different shapes and sizes. Some of them are applicable for circuit boards and others for much higher values of currents. We can see here a stud mount. There's the gates, the smaller wire, and the cathode, the big thick wire here. This is meant to conduct fairly high value of current. We can see they come in puck style, very similar to larger diodes, and they can be mounted to heat sinks and things like that. Light-activated SCRs are yet another type of SCR that does exist in the industry, and that's where, if there is a gate terminal, the presence of light can be adjusted to trigger the SCR on. Sometimes if there is no gate terminal, it is purely triggered on by the light alone. And finally, here is a basic breakdown of showing a data sheet for a SCR, often known as a thyristor. So SCRs, thyristors, they do have similar, or they are used interchangeably, same word, or different word, I should say, for the same object. So remember, an SCR is similar to a diode in that it conducts current in one direction only. It only conducts when momentary pulse of current is applied to the gate, and it continues to conduct after the pulse and until the current A to C drops below the holding value.